So let's review the problem from Chapter 9 on the final exam. You'll notice that what we're trying to do here is to determine the centroid of the area, which is highlighted in blue. Along the vertical dimension, it's bounded by a straight line, which is of length h. Along the top dimension, it's bounded by a horizontal line of width a. And along this dimension, it's bounded by a parabolic curve where any point measured from the x-axis, y, is given as a function of x according to this quadratic relationship. So if I have a given value of x, I can plug it in and I can compute my y, and that gives me kind of the relationship that bounds the lower end of this blue surface. Now, when I approach this problem, if I were to do it myself, I'm going to actually show you the way that you might see it done if you were to explore some resources online in order to solve this problem, because I want you to see that these aren't always the best approaches or the best way to do things. So remember that you can always compute the total area of this rectangle. The rectangle is width a, height h, and you can get the area in blue by subtracting away the area of the rectangle less this area which is highlighted in white. And the reason you might want to do that is naturally you could actually segment this into infinitesimal rectangles, which are vertical, and use the same approach that we spoke of last time. And the main value of it is it would allow you to naturally, since you would be integrating an x there, it would allow you to naturally express any expression involving y directly as a function of x, because that's the form that you're given this equation in. What we'll find is that the way the book is suggesting to approach this problem is to segment into horizontal rectangles and rather integrate all this area in blue directly, which we'll do by allowing y to vary from 0 to h. And when we do that, what we're going to find is when we have a given rectangle, if we're allowing y to vary, we can get the y centroid very easily. But in order to get the x centroid, we're going to have to manipulate this equation. It's going to involve a square root. And it's not going to be a pain because it's still going to be a power rule integration, but it's just going to be a little uglier than it has to be. So here's the way that you want to set this up. If you were to attempt to determine the centroid of the shape, which clearly is going to be more towards h than 0, and it's going to be more towards a than 0, so somewhere up here, the way that you could do it is find the equivalent centroid of each of these little horizontal rectangles and use those formulas that we've used previously. You notice that any infinitesimally wide rectangle located at some point y is going to have a y centroid, which is denoted as y tilde by y, and an x centroid if x is defined as basically the point along the curve at a given y, then naturally the x centroid will just be x divided by 2, because that kind of defines the width of this rectangle, and the centroid of a rectangle is always here in the middle at x divided by 2. But the issue is, if we're going to integrate versus y ranging from 0 to h, we won't want to have an expression that involves x. We'll want to express x as a function of y. And this equation that we're giving is y as a function of x. So the first thing that we need to do is actually manipulate this and solve for x as a function of y. And that's the first thing that I'm doing here. X is a function of y. I can solve that by simply getting the constant over the other side, which I do by multiplying by a squared and divided by h, and then taking a square root of everything. So that's what this is showing here. Now, when I take, and I will correct this right now before I forget, just a little typo, when I take the square root of a squared there in the numerator, of course, that will just be a. In the denominator, the square root of h, we have the value of h, so we can plug it in, but symbolically, we can just write it as root h. The key point is a and root h. This is just going to give us some constant for given geometries. I've chosen to write y to the 1/2 power rather than to show the square root, because as I mentioned, most people are comfortable taking antiderivatives of power functions. So if that is a power, we know we can use our rule of just adding 1 and dividing by the new power. So this is just a way to get x as a function of y. So we know that the centroid of each of these little rectangles is going to be at a given y, whatever the x coordinate is, divided by 2. That's what this is showing. And we know that we can write the x coordinate as a function of y always using this formula. So if you notice, the centroid is simply this formula with an additional factor of 1/2. The y centroid of this rectangle is just whatever y location you're at, and we're going to vary that from 0 to h in our integral. And the area of this slice is just going to be its height, which is dy, times its width, which is x. That width x will vary depending on where you're at in y, and we can express that as a function of y, again, using this formula. So it's just this formula times dy for the width. So hopefully that makes sense to everyone. So whenever you have x bar, y bar, and dA, it's really just going to be a matter of going and using your formulas on the next page. And that's exactly what we're doing here. In order to determine the centroid about the y-axis, which we said is probably going to be along a line that's somewhere nearer to a than 0. I take and I divide by this total area, so I'm just going to integrate. Since dA is expressed as a function of infinitesimal dy, I will integrate from 0 to h, this function, pull the constant out, use your power rule. In the numerator here, notice that the centroid is expressed as a function of y, and it looks basically just like dA, because remember dA was just x dy. This is just x as a function of y, so it's x. But you have this additional factor of 2 here. That's coming from the fact that the centroid is halfway over on the rectangle. So just do your math here. Just be careful. Pull the constant out. A squared, when you have root h times root h, is just h. So a squared divided by h, and then you have your 2. And if it makes it easier on you, just put in the numbers for a and h. They gave you what those are. A equals 6 and h equals 12. So you might find that may make your life a little bit easier. You might not want to, at this stage, when you're taking the square root of h, like don't round the square root of 12 to whatever number that is, somewhere between 3 and 4. But leave it as just root 12 for now, because in some of your calculations, you'll have root h times root h, which would just be h. So to just make your life easier, to leave it like that for now. So hopefully this shows you how to get this problem set up. If you choose to integrate along y, you can do it and choose to integrate along x, but the quantity, the area that you're finding, is not the area that you want directly. It's the to get the area that you want, take the area of the rectangle, h times a, and subtract away that area you're computing. But again, I want to be clear. Only do that if you don't do it the way I'm showing you here. If you do it the way I'm showing you here, this would yield the area directly. It just has that little bit of a pain because you need to manipulate the equation that you're given for this lower bounding curve, since it expresses y as a function of x, to be x as a function of y, since you're integrating in y.